This lesson surrounds nuclear physics and nuclear reactions from the physics point of view. Now we're going to start by looking at Einstein's mass-energy equivalence. This is kind of the basis of nuclear reactions and the energy that we get from those nuclear reactions. Einstein said that energy and mass are the same thing. They're just in different forms, which is where the E equals mc squared comes from. Now your reference table has change in E equals change in m times c, which basically means that how much your mass changes determines how much energy is released. Now when we're dealing with this, and especially in nuclear physics, we deal with these really small masses. Okay? So these really small masses are kind of icky for numbers. You know, you get some really small, tiny number of 1.74329 times 10 to the negative 31st or something like that. That's a really small number. Not very much fun to deal with. So we deal with a lot of atomic mass units. Atomic mass units has a conversion of 1.66 times 10 to the negative 27th kilograms. That's one atomic mass unit. Now you can also use this whole E equals mc squared and get one atomic mass units in electrovolts, or in this case mega electrovolts, which is very useful, especially if the answer is asking you for the value in electrovolts or mega electrovolts. You can just plug this in for m, or at least do your conversion factor, because if you have, let's say, 2 atomic mass units, then you'd have 2 times 931 over c squared mega electrovolts. Okay, so you'd have twice the energy, but that works out real nicely when you're dealing with that kind of stuff. Now, nuclear reactions. We gotta be a little bit familiar with chemical reactions. With nuclear reactions, there are 2 numbers attached to the type of element. So you have your element, and then you have 2 numbers. The top number is your atomic mass. It's your protons plus your neutrons. The bottom number is your number of protons. Okay. Now you might hear the word nucleons. Nucleons are just everything that make up the nucleus, which in, every case is the protons and the neutrons. Number of protons determine the type of element. So if you have 1 proton, 2, 3, 4, that will determine what type of element you have. The mass number does not determine the type of element. If you have a mass of 23, that does not necessarily mean it's going to be sodium. Okay, it could be something else. But if it has a number of protons of 10, if it has 10 protons, it will always be sodium, no matter what its mass is. Now, binding energy. This is where the chemical reactions, or the nuclear reactions, combine with Einstein's mass-energy equivalence. They found this really interesting thing, that if you take the sum of the parts, you would expect it to equal the whole, right? So if you had 2 protons, 2 neutrons, and 2 electrons, and you added their masses together, you would expect to get a mass of 2.016489. Now I got these numbers are constants. Okay, this is the accepted mass of protons, neutrons, and electrons in atomic mass units, and I'm dealing with atomic mass units right now. You would expect, if you put all those together into an atom, they would have this mass right here. But it doesn't. And that's where people are like, oh my, that's interesting. The mass is actually a little bit lower. Einstein theorized that the mass becomes energy which holds the atom together. So if the mass is actually a little bit lower, 2.009 rather than 2.016, the amount of energy needed to bind it is the difference in the energy, or difference in the mass, times c squared. I put it into megaelectrovolts for the conversion. Okay, rather than 0.0074689 atomic mass units, I found it in megaelectrovolts. Okay, so that mass that we don't measure becomes energy holding the atom together, holding all those positive protons which repel each other in the nucleus. Now there are different types of nuclear reactions that we're going to look at. Type 1 is decay, radioactive decay. Now there are different types of radioactive decay. There is alpha decay. Alpha decay is where you eject or produce an alpha particle in your reaction. So alpha decay will always produce a 4,2He. That's an alpha particle. So this is an example down here of alpha decay. You have something, it reacts or decays and produces an alpha particle with something else. Beta decay ejects an electron and also a neutrino, or an antineutrino, which has 0 mass and 0 protons. So it kind of doesn't have much of an effect. Sometimes it's included, sometimes it's not. Positron decay is an anti-beta particle, which means it's the opposite of a beta particle. So rather than being a negative one, it's a positive one. And then there's gamma decay, which is 0, 0. You may also encounter protons and neutrons decaying. Those look like this. Now, within a nuclear reaction, all nuclear reactions have mass conserved and charge conserved, which basically means your atomic mass, which is the top number, is going to be the same, and the bottom number is going to be the same. When I say the same, I mean on either side of the reaction. The sum on this side of the reaction, the sum of the reactants, is going to equal the sum of the products for mass and for charge. So, for example, on this side, 238 equals 234 plus 4, right? 238 equals 238. Check, that's a good reaction. 92 equals 90 plus 2. 92 and 92. Check. If you're dealing with a beta decay, so an electron, you have a negative 1. Okay, you're going to take that negative into account. So it's going to be 7 plus negative 1 would be 6, which balances the other side. So for example, down here, 238, 234, you don't know why? Well, y has to equal 4 for the two sides to balance. 92 plus x and x plus 2, x must equal 90 for the two sides to balance. Now these nuclear reactions release energy along with their decay. That's why we have nuclear power plants. Okay, we know energy doesn't just appear though. This is one atom, right? You know, one atom just kind of splits up and becomes 2. Where does the energy come from? It doesn't appear, doesn't, just go poof. It comes from the energy released due to a mass change. So what you do is you take the mass of the reactants minus the mass of the products times c squared, and that tells you how much energy was released. And the energy released is symbolized by Q. So if you know the atomic mass units of the product and of the reactants, you take the difference and you multiply it by c squared, and you'll get the amount of energy released. You can find Q that way. Now, type of nuclear reaction 2, fission. Fission was discovered in 1938 by Hahn and Strassmann. I like this because I grew up on Hahn's Road, H-A-H-N. Okay, so fission happens when a slow neutron or a thermal neutron enters a nucleus. So you have a neutron entering the nucleus and it's captured into the nucleus and it makes the nucleus unstable. and it splits or fissions with a large release of energy. Fission has a huge energy release. Fissionable materials are like 235 uranium and 239 plutonium. Okay? So those are examples. Here is an example of a fission reaction. You have some big matter, a neutron is entered, and it splits. And then you form two elements and actually three neutrons also exert. Now that extra neutrons is why this would be considered a self-sustaining chain reaction. And nuclear power plants use self-sustaining chain reactions. Basically, by producing more neutrons, you're opening the field up for 3 more reactions. So you can have more 235 uranium plus one of those neutrons. And then you can have another reaction, and another reaction, and another reaction. And as long as your uranium lasts, it will continue happening. Another type of nuclear reaction is fusion. Fusion is what happens on the sun. And I always remember fusion, sun. Okay, they both have U as their second letter. Fusion is a nuclear process in which a light nuclei, so a small nucleus, fuse or join. So you got two small nucleuses and they fuse together or join together, and they release energy in the form of 10 to 20 megaelectrovolts, which is quite a bit smaller than fission, which was 180, give or take. Okay, but fusion also deals with things like hydrogen, which we have quite a bit more of. A light nuclei must collide before they fuse. So these two nuclei, if they're going to fuse together, they're going to have to come together with quite a bit of energy and pressure. They're going to have to hit pretty hard. This requires a lot of kinetic energy and a great deal of pressure. One of the ways to achieve this is high temperatures, and that's what the sun does. The sun is at very high temperatures, millions of degrees. And this allows for fusion. Another example would be a hydrogen bomb. Hydrogen bombs work with fusion. Now let's look at an example. The process that powers the sun and upon which all Earth is a fusion reaction. Show that this reaction releases energy, how much energy is released per proton, and use the fact that M alpha equals 4.0015 U. Ignore the mass of the electron dash neutrino. Now to find the energy released, you're going to have to use E equals mc squared. So we're going to need to find the change in M. Oh, hydrogen 1,1, that's another way of showing a proton. One proton, mass of 1. So there you go. That right there is a proton. This has the same mass as an electron. Okay, it's an anti-beta particle, but same mass as a beta particle. And this is an alpha particle. Alpha particles have a mass of 4.0015. So now we take the final mass minus the initial mass. So final mass is 4.0015 U plus 2 times 5.486 times 10 to the negative 4th. Okay, that's our final product, minus 4 times our initial, which is a proton, of 1.007276. So we get a change of energy of 0.0265. It's negative, so your energy is going down, so your mass is going down, so you're releasing energy. You can take your equation. I'm putting it into megaelectrovolts. So take your atomic mass unit, put it into megaelectrovolts, and you get 99.4 megaelectrovolts of energy released. And for per proton, you just divide it by 4. Good luck!